Christmas always makes me remember that we live in a world of increasing connectivity. This connectivity can be found on many levels of nature. Human beings are connected through human society, which can be thought as a set of interactions between individuals, but also through the internet, the social networks, and many others. At the same time, humans and other animals are connected by food webs, which represent predator-prey relationships. On an even lower scale, the functioning of our brains relies on the connection between a huge number of cells named neurons. All of these examples are collected in some abstract sense by the notion of network. In this series of videos, we will discover together how networks can be used to model many interesting properties in large systems. Welcome to Critical Point. Every now and then, we cross systems that are composed by a huge number of individuals, which are connected in some specific sense. For example, society is formed by individuals that are connected by relations of social interaction, friendship, family, work, sexual encounters, etc. Another example of this kind of systems includes the Internet, a vast connection of computers that exchange information. These systems might be studied in several ways. First, by attending to individual components, studying for example the psychology of every individual in a society, or studying how each single computer works. Secondly, by attending to the links between the components, studying the nature of social interactions or studying how a computer can receive and transmit information. Last but not least, by attending to the pattern of the connections between components, that is, studying the structure of the web in which individual components are entangled. This is the way of the way of the complex networks. To study this pattern of connections, we must focus just on the mathematical background of a network and not on the details of the individuals or their connections. Thus, we can forget about what individuals are and just represent them by points. In the same way, we can forget about what these links and relations mean and just picture them with edges connecting points. I know what you're thinking, this looks like a bad episode of Art Attack, but the structure we are left with is actually what scientists call a network, or in mathematical texts, a graph. I will use both words indistinctly since there is no much difference between any of them. This mathematical model keeps just the essential information to understand the pattern of the network, disregarding other details. However, sometimes we can endow these structures with more details by weighting the edges of the graphs, or using directed edges. In the first case, we specify with a certain number the strength of the interaction represented by the edge. For example, if we represent roads in a certain country by a network, a weight could represent the distance between different points or the money that will take you to travel from point to point with your car. Also, since some roads might only go one way, we can talk about directed edges, edges that work only in one sense, but not in both. For this video, we will center in the easiest example, which is the one that has neither weights nor directed edges. This type of graph is usually called a simple graph. We will start by studying the concept of adjacency matrix in simple graphs. In order to aid me with this noble duty, I have created this artificial intelligence, which I have named S.I.R.I. That stands for Semi-Intelligent Registered Imitation. How are you doing, S.I.R.I? Are you ready for another video of complex systems?
Okay, I found this on the web for psychologists to talk about this complex existence. Check it out.
Well, it's a work in progress, you know. As we said before, a graph is just a collection of points, which we can label with numbers, and a set of edges connecting points. This information can be stored in a compact way using the adjacency matrix, which is defined in the following way. Hey Siri, show me the adjacency matrix.
Okay, I found this on the web for the signs of matrix. Check it out.
Oh my god.
Well, in what follows I have disabled the voice recognition of Siri, and I will work on it for the following videos. Anyway, this is the definition of the adjacency matrix I wanted to show you. This might look a bit technical, but let us see an example to understand what it means. For that, let us suppose we want a network representing who fights with whom in the Star Wars prequels. The main characters of the prequels are Darth Maul, Count Dooku, General Grievous, Darth Sidious, Qui-Gon Jinn, Obi-Wan Kenobi, Anakin Skywalker, Yoda, Mace Windu, and of course, the Mastermind, Jar Jar Binks. We fill the network putting edges between people that have fought each other. For example, Darth Maul fights Obi-Wan and Qui-Gon, so we add those links. Following this way, we get to a graph that looks like this. Labeling each character with numbers from 1 up to 10, we get this abstract representation. Now we consider a matrix that is filled with 10 times 10 zeros and put 1s if A and G are connected. For example, since General Grievous and Obi-Wan fight in that famous scene where Obi says, "Hello there!" we know that the vertices 1 and 4 are connected, and hence we put a 1 in the first row, 4th column. In fact, since we are not considering directed graphs, 4 and 1 are also connected, so we might put a 1 in the 4th row, 1st column. We can keep going and complete the adjacency matrix this way. Note two important properties of the adjacency matrix. First, it is symmetrical. This means that the element on the row number A and column number J is the same as the element in the row number J and the column number I. This happens because we are considering non-directed graphs, so if I and J are connected, so are J and I. If instead of using the relation who fights with whom, we had used the relation who kills whom, this would have been a directed graph, since I being connected to J, which means I killing J, does not necessarily mean that J is connected to I, which would also mean J killing I. For example, because Obi-Wan kills Grievous, we would have A sub 4 1 equals to 1. But because Grievous does not kill Obi-Wan, we would have A sub 1 4 equals 0. The moral is that non-directed graphs have symmetrical adjacency matrix, while directed graphs in general don't. Second, the diagonal elements are 0. This is obvious in this example, since one person cannot fight themselves, but there are graphs in which you can have loops, that is, points that are connected to themselves. For example, in regulatory circuits of gene transcription, you can have both self-activation and self-inhibition, meaning that there are genes whose mere presence affects positively or negatively on themselves. Also, in ecology, if we represent a graph in which points stand for different species and edges represent the predator-prey relationship, you can have loops representing cannibalism. Simple graphs, which are the example under consideration here, do not have loops, and hence have diagonal elements equals to 0. Moving on, we can also realize that if we sum the elements of a given column, say the fourth, of our adjacency matrix, we get the number of edges that start at that given vertex, the vertex number 4. In this case, we get that the number of edges starting at Obi-Wan is 4, since Obi fights 4 guys in the movies. He's such a badass. The number of edges starting at a given vertex is called the degree of that vertex. Thus, the degree of the vertex number I can be written in the following way, as the sum of the elements of a given column of the adjacency matrix. In a more compact way, if we denote by 1 the vector that has all 1s, using a bit of linear algebra, we see that the vector of degrees can be written in this way. Many other interesting formulas can be expressed in terms of the adjacency matrix and its powers, like these ones over here. Let's analyze them in detail. The first one tells us that the number of edges in a graph, which we denoted by the letter E, is just the product of the transpose of the vector 1 times the adjacency matrix times the vector 1, all of it divided by 2. This formula is very easy to demonstrate, so I leave it to you to prove it, since there is no better entertainment for a Saturday night. To understand the second one, we must first introduce the concept of path in terms of graph theory. A path in a network is just a sequence of connected vertices. For example, a possible path from general Gribus, the vertex number 1, to Darth Sidious, the vertex number 8, would be moving from 1 to 4, 4 to 6, 6 to 7, and 7 to 8. But there are other paths to get to Darth Sidious, for example, going from 1 to 4, 4 to 5, 5 to 2, and 2 to 8. To know the number of paths of a given length, let's say 4, that connect general Gribus to Darth Sidious, we can do the following. For a path of this kind to exist, we must have 3 vertices. Let's name them like this, such that the elements of the adjacency matrix connecting each pair of successive vertices is non-zero. Mathematically, we must have the next condition. Because the only values that the adjacency matrix can take are 1s or 0s, saying that all elements must be 1 is equivalent to saying that the product of them is 1. Thus, we arrive to the next expression. Because A, B, and C are arbitrary to have the total number of paths, we must sum over all possible choices of A, B, and C, which give us the following formula. If you have studied a bit of linear algebra, you will recognize this expression as a product of 4 matrices, meaning that the number of paths from 1 to 8 of length 4 is just the element 1, 8 of the matrix A to the power of 4. This matrix is sometimes written in this way, and it is a matrix whose values represent the number of paths that join the vertices A and J that have the length 4. In general, it is easy to prove that the element A, G of the adjacency matrix to the power of R represent the number of paths joining I to J that have a total length of R. This is what we stated in the second formula. Finally, the third formula can be deduced from the second very easily. In this formula, the number T stands for the number of triangles in the network. A triangle is just a path that links a vertex to itself, a loop, having a length equal to 3. Hence, the number of loops of size 3 starting at a given vertex I can be calculated with the second formula in the following way. Summing over all possible vertices, we can get the total number of triangles, which is this expression over here. This formula is the sum of the diagonal elements, that is, the same row and the same column of the matrix, which is something that mathematicians call the trace of a matrix. Wait, but there is one thing we didn't have in mind. Let's go back to the S.I.R.I network. If we calculate by inspection the number of triangles, we see that there are exactly 2 of them, 4, 6, 1 and 4, 5, 6. If we calculate the trace of the cube of the adjacency matrix, we get the following. Why does this occur? I encourage you to pause the video and think of this for a while to see if you get to the answer. You already have it? Look, the thing is, this formula over here does not have into account the order of the vertices. That is, if we change the order of this product, I get to the same expression. This is equivalent to stating that this expression counts repeatedly triangles that are the same one, such as 4, 5, 6, or 6, 4, 5, or 5, 6, 4, etc. The number of possible reorganizations of the vertices is 6. 3 of them come from looking at each vertex of the triangle, and 2 came from the possible ways to walk through the triangle, in a clockwise sense or in the opposite. Anyway, I think we can call it a day. I hope you liked it and that you have seen some interesting properties of the adjacency matrix. By the way, if you do not want this little dog to be sad, you should like this video and subscribe to Critical Points!